We are the Durfee Chime's design group, and our sponsor is Dr. Cory, and our advisor is Dr. Ben Vile. Our group consists of myself, Yuri Sakayev, Joseph Costa, Tanner Studley, and Alex Lewis. And we had a very interesting design, I think. So for this presentation, we're going to explain some of the engineering concepts, and we're going to talk about, we're also going to simplify our process, just so everyone gets an understanding of the process that we took and everyone follows along with what we've done. So our requirement for this design was to expand the capability of this tower. This tower is 48 to 50 feet tall. It's located at Durfee High School, and it's absolutely beautiful. This was recently built. I know Dr. Cory spent a lot of time working on it, and our task was to create a wireless keyboard and a wireless button for this system. So, go to the next slide. So this is what the panel box looks like. Over here on the left-hand side, that's the entire panel box, and if we look to the right, this is where we're connecting to the system. So one of the major requirements is actually making sure that our system is not interfering with the existing system. So if I go to the next diagram, we want the button to be wireless, we want the keyboard to be wireless, and possibly incorporate a playback system if we have time for that. So one of the technical requirements is that it has to play with a range of at least 250 feet, right? So that's far enough to be in the booth while activating the bell, because the button should activate the largest bell during the football game. So this is what the system looks like without anything installed. This is how it was created. And over here we have a computer talking through a USB to a Turtle Beach interface, and this interface controls the bells right now. So every single day, at certain times of the day, it will play the bells. And it goes to a relay through a MIDI, which is very important, and it goes to the relays. The relays will ground certain components, and then it will activate the actuators, which work on 185 volts. So this was last year's design. One of the major concepts that they included was in removing this one wire. The purple wire is removed, and that means the new system, or the old system, would have to go through their design here. And if the system ever failed, the original system from the Turtle Beach interface wouldn't be able to play any bells ever. And also the system isn't very stable, it's very old, so we don't want to mess around with that just in case it stops working, right? So moving on, this is what we created, right? So we're going into the system parallel. So we're not interfering with the original system. We have a button transmitter, a keyboard transmitter, talking to a receiver, going through a transistor relay connecting to the 14 terminals. So our project can be broken up into three modular design aspects. So that incorporates the MIDI, which is the signal used for the communication interface. Musical instrument digital interface is what MIDI stands for. And the XPs, which are the communication components we use, and the terminal relay. So we actually all worked on different parts to speed up the process. And talking a little bit about MIDI, if we look at this wire at the bottom, a twisted pair of wire, and we pretend that one end was connected to our keyboard, and the other end will connect to this MIDI input, this is where we're receiving the signal. So our signal will go through this opto-isolator, and we will get a 31,250 bit per second signal that we're receiving and then sending out to the receiver on the side of the bells. So a MIDI is a unidirectional serial interface. It's asynchronous, and it uses a 3-byte packet, channel, pitch, velocity. And the difference between MIDI and a digital audio signal is that it actually doesn't hold the extra analog signal, which is why it's so popular amongst music. It's very convenient, it's very comfortable, and it's very straightforward, which is why we chose to use it and why our keyboard runs on it. There you go. Okay.
As well, for our project, there were different alternatives that we had the choice of being able to use. This has to do with the output of the system from our receiver end to the bell pins, right? We started with a decoder as our design choice. It was simple in implementation, where the code wouldn't be too complex. devices were very simple. It only needed 6 pins, simple logic. However, there was issues where it wouldn't be able to play chords effectively because each bell needs at least 100 milliseconds to be able to play. It needs that long to be grounded. The issue with that is the decoder can only effectively ground 1 bell at a time. As well, we could speed this up, but again, the bells wouldn't play or wouldn't play too softly. To try to solve this, we had a one-shot design as well, which is sort of an add-on to the decoder. The decoder is still used, the same code is still used, which is a great thing. The one-shots allow the signal to be extended. So say we send a 1 millisecond signal, a 1 millisecond pulse from the decoder. The one-shot's extended to 100 milliseconds. This works for each bell independently. So we can have the decoder running at 1 milliseconds for each signal being sent, and the bell will play accordingly. And the only issue will be that the same bell can't be played rapidly, which is fair. Many bells, however, can be played rapidly. The issue, however, is it's physically complex, where there's a few things that can go wrong. It's too large for the current boxes, and also located overall, and it also adds to cost. The third idea we had was to use a shift register design, right? Now, this is 2 daisy-chained shift registers, each having 8 outputs, adding to 16, 2 of which will be unused, naturally. It only needs 5 inputs, which is a very nice thing. It's compact. Its chords would be possible since you're able to shift bits into it. And once all the bits are taking up 16 slots within the shift registers, you can then have it released into the bells, essentially allowing us to ground or not ground multiple bells all at once. So it can work quickly and effectively. The only issue, however, is it adds more complex logic to the code, so the previous code would no longer be useful. We'd have to adjust it. More attention would be needed for timing, particularly for these chips. And while we were trying to develop this, we also came up with an even simpler solution. What these shift registers are usually for is to add many pins to be controlled via only a few pins. So 16 or more pins can be controlled using only 5 ports. But in our case, it's not an issue since our PCB is able to have 14 plus outputs, 15 plus. So our actual solution, what we use, is to just use the PCB outputs itself. We're using NPN transistors as well as the resistors you see above. There's no extra components, it's cost effective, it's compact, and chords are possible through edited code. It would have to be adjusted based off the decoder code, but it would be simpler to implement than the shift registers because we wouldn't have to take account of shift registers. Then there was also the button. The original request was to have the button be able to play the largest bell. It's straightforward. There was a recent request, though, if the bell could possibly if the button could possibly play a set bell, and the set bell can be swapped out with another bell by pressing an alternative button, right? So you can just shift through different bells. We did develop code for this, and we also developed a design. Unfortunately, for favor of time and other projects we had to handle at the time, we had to leave it unfinished. But there was progress towards it. Then there was also the XP communication that we had between the PCBs. In this case, we tried to use API mode, which would allow us to have easier access to troubleshooting devices. Where it allows us to not only see the sender of a signal, but it also allows us to see how strong the signal was, how long the signal had to travel. It also allowed us to use packets to have all this information in a suitable format for us to be able to read. And also see if there were any errors in signal sent. However, it wasn't used perfectly, where we weren't able to get it to work completely. There are also obstacles using XPs, or wireless in general. The big one is that there were obstructions between the signal. Particularly, there was a metal plate between where the receiver XB would be and where the keyboard and button would be played. This metal plate got in the way of the signal, which highly reduced the range. So we have to make a shelf to raise it above, high enough over the plate, where it would have the accurate range. The level shifters also had to be used, where the XBs are only able to use 3.3 volts, where our PCBs use 5 volts. We had to use that to protect the XBs and allow them to stay operational in our PCBs. We'll give the PCB design to Tyler.
Okay, so this is one of 3 PCB designs that we made. This is MIDI that will take in the MIDI signal from the keyboard. Up here deals with the power, brings 12 volts down to 3.3 volts. Up here is some headers that will be used for debugging issues. This right here deals with the MIDI signal, transfers it to serial. This is the microcontroller. We used the ATmega 2560 for 2 different serial ports. That one was for the XB, one was for the MIDI. And right here is where the XB plugs in. On the left side, that's the populated PCB that we made, and that's currently being used in our design, and that's the enclosure on the right side. This is our second PCB that we made. This is multi-purpose. This is for the receiver and the button. They're 2 separate PCBs, but they're used for the same thing. So up here deals with the power again. There's a 5 volt voltage regulator and a 3.3 volt voltage regulator for level shifting, and for our previous design of using a shift register that required 5 volts. Right here plugs into the transistors that will be talked about in the next 2 slides. Right here is a ATmega 328P, and it deals with the serial, takes it in, and then sends it to these, turns them high. This is where the XP plugs in, similar to the last one, and underneath it is where the level shifting occurs. So this is the populated version of the receiver. This is the transistor PCB that grounds the the relays in the Dr. Cory system. This is where it plugs into the receiver. Right here is the NPN transistors, and right here is the screw terminals. The screw terminals that we use are 2 parts. There's a male and a female for an easy disconnect in case our customer wanted to disconnect our system from his. And this is the transistor board populated, and on the right side is the enclosure with the receiver connected to the transistor board. And these are all the boxes next to each other with everything inside them. So this is the code flowchart. It can be separated into 3 different parts for the 3 different subsystems. So the MIDI starts, initializes, checks to see if a note's played. If it's not, it keeps on looping until a note's played. If there is a note played, it determines the pitch, which is the value of the note played on the keyboard, creates the packet with the correct value, and then sends the packet to the receiver. The button starts, initializes, creates a packet, sends it to button. It's only meant to play 1 bell at a time, so the value won't change at any time. And so checks if the button was pressed. If it does, you send the packet. If it doesn't, it just keeps on looping until the button's pressed. And on the receiver side, it starts, initializes, sets all the pins low that will be sent to the transistors. Then it checks to see if there's a packet available, checks to see if it's a ZigBee packet, which is a type of packet that we send, and then if it is, it sets the pins high for 100 milliseconds, and then sets them back low so they can be grounded for 100 milliseconds.
So I'm going to discuss some of the test plans. It's a little more clear over here. So one thing we have to work on is make sure we can send the MIDI signals, receive the MIDI signals. So this is more of the wires, reading the opt-isolator, and then we also wanted to make sure we're able to send the packets of information. And one thing that we didn't cover is acknowledging that a packet has been received. So that's the receiver sending a message back to the transmitter to tell it that it has received the signal. So the only flaw you can have is if we're sending a signal and then we try to send the signal again and we're out of range, and once we start coming in closer to the bells, it's going to play 2 bells simultaneously because it can't respond back to a transmitter that the signal hasn't been received. And sending the MIDI pitch, so understanding which note needs to be played, and then the final test is going to Durfee and verifying that everything works. So this is our, so green indicates the expected time on our design, and then blue is the actual time spent, and obviously we spent the whole semester working on it. And Dr. Van Val actually brought up Hofstadter's law, which means that everything will take longer even when you include Hofstadter's law. So it's an infinite loop. Nothing's ever done. It can always be improved. So there's always room for improvement. And you're good.
So our budget we had was about $200 at the max, and we spent just under that at $197. And the only reason we could do that is we used many products from the past year's project. And while we had the option to do the recording capability, we just ran out of time and could not finish that. But if we updated our code or changed to a different keyboard, it would be a lot easier to implement that option. In summary, we were able to achieve the desired customer requirements under all the necessary conditions. Some future improvements may be made. We could change the transmitter, the receiver, and optimize it a little better than we have. Out of the lessons we've learned that when scheduling a design project, account for all the extra factors that could pop up. Lots of things happens that we just didn't account for at first. Our time ran a lot later. We should update our work as soon as possible when our changes are made to avoid confusion. Organize work done for project partners. Always listen to advisement from everyone else in the group. Review all our own work, leaving substantial time for the testing and the troubleshooting as you saw on the plan schedule, and involve the customer with the project and note their input too. Here we have a video going over how the keyboard and the bell will work.
This is the project. This is Tanner, saying hi, Tanner. I'm gonna back up. Let's do this thing.